So just one small correction, that this person is, these are both under null hypothesis. Then, so it's important, I didn't say it last time, is that under null hypothesis, under H naught, which is H transpose beta is equal to 0. Under null hypothesis, this is these facts are true. That is, the R naught squared, R squared is sigma squared, and this will also go some way in showing the proof of the F distribution, which also we will complete next time. But as of now, let's just try to sort of do the theorem of this proof. So I'm doing it in generality in one shot, so that this is available for all dimensions and n and so on and so forth. Let me just do this proof. Okay, this involves some facts of linear algebra. So I'll assume that you may know it. If you don't know it, we'll come back and maybe send feedback on the class discussion group, then we'll come back and sort of fix it. Okay, so first thing we do again is SVD. So you take X, X is what now? N cross M matrix. That's what the linear model is. We'll do an SVD of it. So SVD will give me what? Will give me, let me start with matrix P on this side. Let's say an N cross N matrix. And I have two diagonal blocks. On this side, I'll have a Q M cross M matrix. And this is transpose. There are two orthogonal ones. And I have a diagonal, let's say here, I'll call it dr cross r, and then there's a bunch of zeros here. 0, 0, fill up this space. Okay. Again, now I'll just write it a little further. I'll think of my P as partition into the first R columns and the next R columns. I'll call it P1 M cross R, and X, the rest is P2. And I'll even partition my Q appropriately into the first. Q1 is the first, maybe again M cross R matrices, because the R is the R column, and then Q2 is the other part that's left. I'll keep it like this. Then I'll immediately know that this will imply that X, the algebra, is just Q1 D Q1 transpose. That's what Excel used. That's easy to see. So now, what do we know? So we know this some facts we keep in mind. We know that H transpose is estimable. H transpose beta is estimable. That's assumption of the theorem. And that implies we already seen that column space of X, H, is contained in column space of X transpose, which is same as column space of X transpose X. This is something we have in, there are two facts we have in mind. Let's keep it in mind. Now, because of this fact, let's call this fact 1 and fact 2. Let's call this as fact 1. We call this 1. Let me call this as fact 2. So fact 2 implies, so column space of H is contained in this. That means there exists a matrix V, I'll call it as N cross K, such that, what happens, such that H is going to be equal to Q1 times, so let me put this as 1 and 2, so 1 come out. So, see, X transpose X, when you do it, the simple exercise, X transpose, when you do it, it'll be X transpose X, and then the P goes away, right? So only the Q remains. That's why you have Q1 times V, right? So we'll put Q1 at the top. So simple exercise, it's a simple exercise here. Linear algebra. Right. And we also know that this matrix has rank K. Very good. So now, I'm after this theorem, but I want to show these two distributions, right? So I have to just work towards it. So just bear with me. Sort of a bunch of linear algebra that I have to do. So then I would do is I put matrix C as sort of the quadratic form Q, the diagonal matrix D that I have, to the -2 times V. So I have to design the special matrix. This is an M cross K matrix, right? Because M cross R matrix, M cross M, R cross R, and R cross K. So R cross K, sorry. This should be an R cross K. Because Q1 is R, right? Very good. Very nice. Now, what does this imply? This implies if I look at X transpose X times C, right? So that's going to be Q1 D squared Q1 transpose. That's what X transpose X gives me, right? And what is C? C is again Q1 D minus 2 times V, right? So that if you just do the whole thing, I just get X transpose X times V is equal to Q1 times V is equal to H. So I've actually found out a matrix C for which X transpose XC is equal to my H. So I've gone a little bit further. Okay. The next thing is going to be what now? Now this implies also let's see also. Look at X times C. And if you look at X times C, what will that be equal to? That will be equal to P1, right? Times the diagonal D, right? I have Q1 transpose, and C is Q1, I have D minus 2 times V. So I'll get it as P1 D minus 1 times V. This is what I have. Very good. So therefore, the column space of X times C, right, is contained in the column space of P1. That's it. And you also know the rank of this is K, so the whole thing will be the rank of XC is going to be equal to K. This is kind of observation. Right. So now a rank of a matrix is K. So what I can do is I can find a basis for the people outside the column space of XC, n minus K people outside. So it's a simple exercise to do. So you can try and do it. You can construct. Construct P tilde. Let's call it P1 tilde. 1 tilde. So this is an n cross n minus K matrix, right? Whose columns are an orthonormal basis. The one orthogonal, I want orthonormal. Orthonormal basis of the orthogonal complement of C. So I'll just put column space of XC and I'll put a per. Right? And inside column space of P1. Right. So now you're just a little bit careful. I have this guy here. So it's inside this. So I'm going to take this in the orthogonal complement inside the subspace column. So I look at that. Now I'll construct a new matrix P tilde, and then I'm almost done to get the result. So this is the key result. That is, I take P tilde, so I've decomposed P tilde to be equal to XC. I put P1 tilde, the next n minus K people, and then put P1 after that. Oh, this is no, I put P2. P2 is the last part, right? Sorry. This is the other part. So I change P to this. I change P to the first key columns to be XC, and then less to be P1 tilde, and the other to be P2. Now, if you noticed, just one small thing, P tilde transpose P, simple exercise, I'll let you figure out, it's not that hard, is going to be equal to, so you'll get, in the first one, you'll get C transpose XC, that's the first entry. Then everybody else will be 0. This will be identity again, 0, 0, 0, identity. That's just by the definition of P1 tilde and P2. And moreover, this is one thing, then this is like P transpose tilde X will be C transpose X. That's the first element of P. Next will be P1 transpose P1 tilde transpose of X. Right? And the last element will be 0 because P2 is off. Very cool. That's what you'll get. So therefore, P transpose tilde X beta, which is what you're after, will be what? Will be, again, this whole thing. X transpose X beta, P1 transpose X beta. But what is C transpose X beta? What was C transpose? That was just H. If you go back here, so there's H. Right? So the first guy will give you H transpose beta. We call this as fact 3. Put this as fact 3. This is from fact 3. Right? And the other one you leave it as other one P1 transpose X beta, you leave it as this P1 tilde transpose X beta. You leave it as it is, and 0 is very good. Very good. So now this I will call it as my sigma. I'll define it to be my sigma matrix. This I'll define it to be a mu matrix. And why do I do that? It'll be clear in a second. So let me just recap a little bit. So I'll just do 2 windows and recap a little bit what I've done so far. We'll come back and do it again. So what have I done so far? The first thing I took was I took an X. Come back down. So what I've done so far, I took my X. I did SVD to it. So I didn't write SVD. Let me write down SVD. So SVD. And once I did SVD, then I plucked out 2 things. One was that how X looked like, this is 1. And by estimability of H transpose beta, I got expression that column space of H is contained in X transpose X. So with both these 2, then I was able to get the fact that H looks like this, Q1V. And then if I look at X transpose X times C, I get H back. And XC looked like P1 D inverse times B, which implied that column space XC is contained in column space of P1 and rank of XKs. So then the key was to construct another matrix P1 tilde, whose columns were outside column space of XC, the orthogonal complement, inside column space of P1. And once I had this, I have a new matrix P tilde. And this property had this property that P tilde transpose P was sort of diagonal like this. So I call this sigma. P transpose X was P tilde this, and P tilde X beta was going to be equal to this. Okay. So now let's try and see how we're going to use this, right? So how we're going to use this now? So the key thing is now, because I want to get distribution, right? Distribution is the key use is following. You define Z to be equal to, Z vector is equal to P1 P tilde transpose times Y. So if you look at the above, P tilde Y transpose above, Y is normal with mean X beta and variance covariance matrix P tilde, right? So it's going to be equal to, this is going to be same as, distributed as normal with variance mean mu vector, and variance is just going to be sigma square times, not like sigma square of sigma. It's going to be mu time and sigma squared times the sigma that we have. Simple exercise to try and check. Because Y is normal with mean mu and variance of sigma squared I. P tilde transpose Y would just have the linear combination, will give you sigma squared. The sigma and mu are from above right here. Right. So once you have this, you're in great business now. This is what is Z tilde now? Z tilde is what the first part is going to be, you know exactly what P tilde Y is going to be like. It's X beta, right? So it's going to be equal to, so it's going to be C transpose, sorry, not X beta, mean is X beta, but C transpose X transpose Y is the first guy. The second component is P1 tilde transpose Y. The third one is P2 transpose Y. Sorry, Put P1 again at the bottom by mistake. So anyway, I've been making this mistake everywhere except here. Let me go back here. So it's P1 transpose, P1 transpose X. And here again, this P1 is above. P1 tilde transpose. I think this is P1 tilde transpose X. This is P1 tilde. Wait, this is P1 tilde as well. Goodness. So it's P2. So again, P1 tilde. P2. And this P2 transpose Y. This is what my Z looks like. Right. Now, you just see, Z is normal. What does sigma look like now? Sigma looks like this, right? Sigma looks like this. So the first component involves this guy. Second component is I with this guy. Third component is I with this guy. That means these are all zero. That means the covariance between these components are all zero. Okay? So the crucial thing is that suppose I think of this as the first part as Z1 to Z1, second part as Z2, the third part as Z3, let's say, right? Or let me call it as Z1, Z1 tilde, because that's the orthogonal complement. Maybe I'll draw it properly. Let me call it as Z1, Z1 tilde as second component, and Z2 as a third component. This is Z1, this is Z1 tilde, this is Z1, Z2. Now, because structure of sigma equal, let's copy sigma equal to this. Copy. Sigma is equal to this. Put this. What do you know? You know many things about, you know several things. First thing you know is that Z1, that's the first guy, is normal with mean. What is mean? How do you mean again? Where is mu now? Mu is here. Right? Let's grab mu as well. Where is this mu? Mu somewhere here. Let's grab mu. Mu is this. Copy. Let's put mu here. Maybe put mu here first, and then I'll adjust in a second. What up sigma is here. Make it a little smaller. Very cool. And mu across. Use this. So what do you know? Z1 is what? Z1 is the first guy, right? Z1 is going to be mean, H transpose beta, and variance is C transpose X transpose C. C transpose X transpose C. First thing, what is Z2 going to look like? Or Z1 tilde going to look like? That's again normal. The mean is second guy, right? This is going to be, I just call it as a, I'll call it P. Okay, let me copy this down. This is going to be this. Copy down right here. And this guy is going to be this, and then this guy is going to be this identity. So I'll call it sigma squared times I. The dimension is n minus k, right? N minus k cross n minus k. Right. And the last guy is going to be Z2. It's again normal with the mean is 0 now because there's nobody there. And the variance is sigma squared. And it'll be I n n minus r cross n minus r. This is what I have. Very cool. R minus k, I'm sorry. So now, and what does you know? You know one more fact, this and what do you know? You know the independence as well, right? You know that Z1, Z2 all independent. Z1 tilde and Z2 are independent. Now I'm ready. I've sort of done this decomposition of P transpose Y, P transpose Y into all these factors, and I'm done. So now I'm ready to prove the theorem in some sense. It's quite easy now. Back here, start here. So if I have norm of y minus x beta. This is what I wanted. This is what R naught squared will look like, the minimum of all these things. And R1 squared is the one with the thing. This is what? This is y minus x beta into y minus x beta transpose. That's the definition. There's no fanciness in this. Now, this, if you just think a little bit, what is y minus x beta? So y minus x beta is just going to be like, if I want to write in terms of z, it's just z minus mu, which I have here, transpose, and I put the sigma here. This is something you check, sigma and z minus mu. What I have. So this is not the right one. This transpose is here. So you can check y minus x beta same as z minus mu. That's not hard to check. That's a straightforward. It's a construction. So once I have this, sigma inverse, sorry, if I have this. So if I have this, then you can get that this is same as, if you split up into the four things, we get Z1 minus H transpose beta. That's the first piece, transpose. And what's in the middle is this C transpose X C inverse, right? So let's call it as, that'll cancel off, I think, to give you Z1 minus H beta, right? H transpose beta. I'll leave the matrix as this, plus the next part is going to be, plus the second part is Z1 tilde minus mu1 tilde. I call it mu1 tilde now. Transpose what was inside. There's identity here. And I'll have, this is just Z1 minus mu1 tilde. The mu1 tilde is exactly this P1, this whole thing. So what's what I call mu1 tilde. And plus I'll have a Z2, Z2, last one, Z2 transpose Z2, because there's nothing in the middle. There's no need. What I have, right? So now I have broken this up into three independent pieces, right? This is one piece, second piece, and third piece. And they're all normal, and I've broken up my norm squared into this piece. That was the whole point of this whole computation right here. Very cool. So start off with what x was. I start with x. What x was, let me make it double and see if that works. Was to sort of get this whole exercise going, right? Once I define my x to be singular decomposition, and I have y is equal to x minus beta, x plus x minus, plug in x, plug in what, plug in beta, you will get exactly, plug in x as this, and plug in all the roots of this, you get exactly what I have. The whole point was to split up this error sum of squared as three normal squares in some sense. So now we are almost there to finish the theorem. We're almost done. So we have R1 squared is equal to what? Is the minimum over beta in Rm and under the null hypothesis. That is H transpose beta is equal to 0, right? And this guy is y minus x beta squared, right? That's what this is, right? This is what the R1 squared is. And so let me write this down here. Since I need this, write it properly here. Let me have the yellow part, and yellow part what? C transpose X transpose X C, the whole inverse. So that's going to be equal to, so what I'll do is I'll take the one without H transpose beta equal to 0, right? So if that happens, then this guy goes away. This guy's already there. So what's left is H transpose beta is not equal to 0. That's what's left on the other side. So it's going to be simple exercise. It's going to be this plus this guy, right? So it's going to be this plus this person right here. So This is the one without that, right? So without that is this plus this guy, right? Plus the last part is the minimum. Minimum over beta and Rm, H transpose beta is equal to 0. And what I have left is just Z1 tilde minus mu1 tilde squared. Very good. So the mu1 tilde is just P1 tilde transpose X beta. Okay. I'm almost there now. So this is going to be equal to R1 squared is equal to R0 squared plus this part. I can choose my mu1 tilde to close this guy, no problem. Right? So this part will just be R1 squared plus Z1 transpose CX C transpose X transpose XC inverse times Z1. No matter. Very good. So that means now I know exactly what's going to happen. Right? R1 squared minus R0 squared independent, and it's sigma squared. So therefore, R1 squared minus R0 squared is like sigma squared chi squared. And the independence of R0 squared minus R1 squared R0 squared also follows the same expression. So unfortunately, the proof is just linear algebra, and then that's why it took so long to do it. So the main thing to keep in mind is that the second fundamental theorem V squared is that the distribution of the one without H0 and one with beta 0, that is going to be sigma squared n squared.